Hey, everybody. How are you, Mel? Aisha, Wyatt, here comes Ella. Great to see everybody today. I hope you're all doing well and had a great weekend. Yeah, Matt.
Hello.
It's great to see everybody, really. Anybody have anything fun they did over the weekend?
Uh, Not really.
Not really. Yeah, sometimes it's nice to have quiet. That's a good thing too. All right, we have a lot to cover today, so I am going to get us started right away. So that we're sure. I built a rotating tank turret out of Legos. That's pretty cool. That's a pretty cool thing to do.
Awesome.
All right, let me share my screen with you guys. There we are. All right. So as always, if you have any questions, this is a good time to ask. If you have questions as we go on through the class, you can ask at any point. Matthew.
So, when we were going through the lessons this week, I was wondering if, because I know that crabs can change color, like they can go from like red to blue and stuff.
Some can, not
Is
all, but
is
some.
that influenced by chemical changes?
Yeah, generally that's influenced by chemical changes. Sometimes animals change color depending on what they eat. If the food has certain pigments in it, then they'll take up those pigments. Really depends on the animal and what what's the cause of that is. But yeah, it's chemical change of some kind or a pigment. Yeah, good question. Mel.
In that same lesson, I was wondering if you dye water, would that be a chemical or physical change?
What do you think?
I was thinking more physical.
You're right. It's physical change because all you're doing is adding color to the water. So that isn't changing the nature. You're not, think of it this way, a chemical change takes apart the molecules into atoms and then rearranges those atoms in a different way. Just adding dye to water doesn't do that. It's just simply adding something. A way you can do it that you can also know is, can you separate it out afterwards? So if you were to just let all that water evaporate away, you'd have a container that just had the dye in the bottom of it because the water molecules would separate out into the air. Yeah, good question. Anybody else? All right, I love it. I love it. Keep the questions coming. All right, can you guys all see where it says physical science there? All right, so I want to talk a little bit about Flexbooks. So I know that it's early. We've just started using this kind of material in these Flexbooks, and I've copied the Flexbooks into the lessons so you don't ever have to leave Canvas. But I want to take a couple minutes just to show you all the cool things that Flexbooks has that are different from the things that I put in the lesson. So let me pull this in. Nope, not that one. Not that one. All right, there we go. Here we are. Okay, so this is the what you guys see when you go into your lesson. So let's take a look at the one that's due on Friday. So it would be this one, September 6th. So you click right there where it says 1.7 state changes, and it takes you to the page where you're going to read your lesson. Now, at the bottom of every one of the lessons, you'll see this yellow box that has the Flexbook pages that I got the content from. So I do make some changes in some of these. Sometimes I add things, sometimes I take them away, sometimes I rewrite them. But you can always see that Flexbook page if you want to. It's always going to be a clickable link down there at the bottom that you can go to. And there's a lot more that you'll see. So this lesson was adapted from these 4 Flexbook pages. I want to click on one of them and let's take a look at what you can see right there. Good, you were going through them. So good. So right here where it says read, that's where the content would come from that you read. Usually I find that's what I put right into the lesson. There's almost always a practice problem set right here. You can take this quiz to see how well you understand the material. You're not, they're not assigned though. You don't have to do these. You're not graded on them, but you can click to see if you understand that concept. And then if you don't do well, you can always go back and read it again. There might be some real world scenarios here. Again, sometimes I put those in the lesson. Sometimes I assign them, but not always, but you can usually go and see stuff like that. There are sometimes these PLICs. So PLICs are interactives that are good quizzes to help review before the actual quiz. Yeah, and Josiah, you'll notice that some of your quiz questions will come right from the practice problems that are in the Flexbook. So doing it in the Flexbook will help you. It'll help you review, and it might also help you with some of the actual test questions. But let's take a look at an example of what an interactive is. So you can see this. So as we drag this button up right here, we're going up the mountain right there. Notice what's happening to the boiling point and the atmospheric pressure as we go up the mountain, right? So you can see some changes there. Now that's all this one does. This is a pretty simple one that you can see pressure and boiling point go down as altitude goes up. There's also a thing that says challenge me that will ask you some questions. Again, it's like a quiz where you can see how well you understand the concept. This also is not graded. These are for those of you who want more. You want to go beyond what I put in the lessons. Nothing that is only found here is going to be on any kind of an exam or a quiz. Now, it might be in both places, but you'll only be quizzed on what is actually in the lesson right here that I have for you right there. All right. Anybody have any questions about those? So once in a while, I do assign some of the things that come from the Flexbooks. Right in here, I might assign a real world scenario, but I make it very clear when I do. Just remember that these things are here to help you learn. You can use them as often as you have time to do so. Evan.
So in the previous assignments that I had, the videos didn't work.
Okay, if that ever happens, let me know. Sometimes links break. I do my best to check them all. Did anybody else have a problem with videos not working? Okay, sometimes, Evan, it's possible that you may have some kind of a filter on your computer. If your parents have a filter with parental controls, sometimes videos won't work for you. Everybody else is saying that they didn't have any trouble. Josiah did, though. I couldn't watch them simply because YouTube is blocked. Yeah, that may be the case. If it is, let me know if you aren't able to watch something either because it's blocked or because you just are having a problem. Maybe everybody is having a problem with it. Sometimes I can find a workaround. I'll find a solution, or I'll tell you that is not, it's not an important video. Sometimes they're just there for supplement to help you understand a little bit better. Yeah. All right. Okay, no problem. All right. Blocking can shut out videos. Right. Yeah, that can definitely happen. Okay, so moving on from Flexbooks, let's talk a little bit about messages when you have a question for me. So if you are going to send me a message through Canvas inbox, which is my preferred method, please make sure to be very specific. Tell me the page number, if it's, something in one of the Flexbooks, or the lesson number, the question number in a quiz, and give me as much detail as you can so I can help you. So don't just say something like, I don't understand question 3 on today's quiz. Well, I don't know which lesson you're doing today because everybody works at different ones. So you have to tell me in quiz number 3.5, question number 7, it seems to say this, but I don't see a possible answer choice because something like that. Just the more specific you can be, the faster I can help you. We don't have to go back and forth with me trying to figure out what it is that you're asking. All right. I told you guys last week that at some point here in the next week or two, I will begin taking off points for spelling and grammar errors. I won't take off a lot of points, just a few. Like maybe in a question, you might lose a quarter of a point in a 5-point question. So it's not going to be a lot, but it is very important for you guys to learn how to use proper grammar when you're doing school subjects. Evan, do you have another question, or is your hand still up?
Still up.
Okay. All right, take it down if you can. Yeah, so I've noticed a couple of common errors. So those are the things that I'm going to talk about here. There's a lot more to good grammar than just what I'm going to require, but these are the things that I'm going to be looking for. So first of all, grammar matters. Proper grammar can save lives. Just putting that comma in there is the difference between eating grandpa and having grandpa over for dinner. So proper grammar saves lives. Here's another cute one. A panda eats, shoots, and leaves unless it's a tactical panda, and then it eats, comma, shoots and leaves. All right, so grammar matters. So what am I going to be looking for? What am I going to be taking off points for? First thing, I want capitalization of the first word of every sentence, the personal pronoun I, and the names of specific people, places, and things. So don't have little lowercase i's in your homework. Now, when you're typing here, if you're writing in this chat box in live class, or you're sending me a Canvas inbox message, do whatever you want. I'm fine with text speak in those. I'm not going to take off any points for anything that you submit that way. When you're turning something in for grading, that's what I'm talking about here. That's when I want you to use capital letters. Always capitalize the first word of every sentence. All right, and the next one is use complete sentences. A sentence, a definition of a sentence is a group of words that has a complete thought. It has a subject and it has a predicate. And usually the predicate is a verb, so we'll say verb. So you usually got a subject and a verb, and the verb is like an action word. So the flower bloomed. The flower is the subject, bloomed is the verb. Bob painted. Even though it's only 2 words long, it's a complete sentence because it has a subject and it has a verb. Please don't, hold on just a second. Okay, so here is another thing that I want. It's best not to begin a sentence with the word because. There are a couple of situations where it's okay to do that, but it's a little bit complicated. So for our class, just don't do it. So the 2 times where it would be acceptable to say with because, number 1 is where if you can use the word since I did something, you can use the word because instead. Since the plant didn't grow, I hypothesized there was not enough water. You could use because the plant did not grow. But it works best to just write it in a different way without starting it with because. The second one is when you're having a conversation with somebody. If I were to say to you, why do you think the plant didn't grow? You could say, because you didn't water it. That's correct. That's fine in these conversations. For homework, though, don't start with the word because. And finally, last rule is punctuation. Sentences always end with some kind of punctuation. If it's a statement, it ends with a period or an exclamation point. If it's a question, it ends with a question mark. So like I said, there are more grammar rules, but these are the ones that I'm going to grade on, that are important for my class. Capitalize. I'm not going to worry about Oxford commas. Yeah, we're going to keep things more general than that. This is not an English class. This is a science class. So I want you to use proper English, but I'm not going to be real rough with grading, except for these things right here. All right, so take a look at this one and tell me which of these is correct. 1, 2, 3, or 4. Yep, number 4, because it capitalizes the first word of the sentence and it has a period and it doesn't start with the word because. Here's one more. Which one is correct? Yep, number 3. Number 3 is correct because let's look at them each. This one doesn't end in a period. Number 2, the lowercase I. You always want your personal pronoun always has to be capitalized. This one has the capital letter at the beginning, capital I, and a period. And this one doesn't begin with a capital letter. Okay. Yep. Yeah. All right. So I have a couple questions for you guys, just so that we can get to know each other a little bit. A couple of get acquainted kind of questions. So you can type your answer right in the chat box there, and I'll do my best to read them all out loud. All right. First question. Using just one word, name something that makes you happy. Lego, hockey, family, racing, friends. Ooh, there we go. Pets, motocross, animals, dogs. Excellent. Sports, animals again. Brain, your brain makes you happy. Sleep, yeah, sleep makes me happy too. That's a good one. All right. What is your least favorite food? Least favorite. Crabs. Bok choy, that's an interesting one. Mushrooms, tapioca, fish, Brussels sprouts. You guys are listing some of my favorites there. Broccoli, yeah. All right, another mushroom and olives, crabs and peas. I'm not a big fan of peas either. All right, here's another question. Hot peppers. If you could have 25 hours in each day, what would you do with the extra hour? Excuse me. Oh, excuse me. Play with my friends, sleep. I like the sleep. That often comes up a lot. Spend time with family, divide it between Legos and sleeping. Half hour of Legos, half hour of sleeping. Have a dog. Yeah, it takes a lot of time to have a dog. Play sports, video games, hang out with family. Excellent, excellent. All right, another one for you. If you could be in the Guinness Book of World Records, what record-breaking feat would you attempt? What would you like to be remembered for? It's a little harder one, isn't it? Biggest motorized Lego creation. How many hot dogs you can eat in 30 seconds? Wow. The best writer in the world. The biggest moron. Most dogs owned. Wow. Wonder what the number for that is. Fastest guitar solo. World's fastest video game speedrunner. Greatest artist. Putting the most spoons on my face. Biggest, oh, get down here. Most animals owned. Rubik's Cube time. Most cats owned. All right, some of you guys want a lot of pets. All right, last question. Using just one word, name something that drives you crazy. Life. Mom. I'm going to tell her you said that, Vita. Styrofoam, yeah. Monkey Brothers, lawnmower. Lawnmower, you mean like having to mow or the sound of it? Talking over other people. Not everything, just a brother. Yeah, siblings. Siblings eventually become your best friends, but when you're growing up, they can be challenging. Loud dogs. Yeah, hopefully my little one won't be too loud during class. We'll see. All right, we'll do a couple more of those next week just to get to know each other a little bit better. All right, so I want to move pretty quickly through talking about matter today. The rest of this week, you're going to be learning about how matter can change its state. So last week you learned about matter, some properties of matter. This week you're going to learn how it can change. And really that depends on temperature for the most part. A couple of other things too, temperature and pressure, but it depends on the temperature, what the changes are that we have. So that we can have plenty of time to do our oobleck, I'm gonna go through this quickly. If you haven't assembled your ingredients to make the oobleck, the non-Newtonian fluid, that's fine. You don't have to. This is an optional activity. And if you don't have quite enough, like if you don't have a cup and a half of cornstarch, you can use less. You can use half of that, which would be 3/4 of a cup. And then you just use half a cup of water instead of a whole cup of water. It's just a proportional thing. So even if all you have is a couple of tablespoons of cornstarch, you can still do it by adding just a little bit of water. And it'll be a small, very small amount of oobleck, but it'll still work. All right, so keep in mind that matter can exist as solid, liquid, gas, or plasma. But the ones that we find commonly on Earth are solids, liquids, and gases. Please remember, everything that has mass and takes up space is made of matter. And all matter is made of atoms and molecules that act as tiny particles. Now, so it is, well, it's actually, oobleck is not all that messy, but it's up to you whether you want to do it or not. It dries pretty easily, and you can rinse that cornstarch on your hands in a minute right down the drain. I just bring a washcloth and use it to wipe it off. So it's up to you if you want to do it or not. So remember that we use this word particles. So the word particles.
How much time is it before it loses its properties?
How much time before what loses its properties?
Oobleck.
Oh, as soon as the water evaporates out of it, it'll just be a pile of cornstarch again. Same as the water that Mel was talking about at the beginning. Yeah, the water will eventually evaporate out of the oobleck, and you'll just be left with a little pile of cornstarch again. Yep, good question. So we're going to use this word particle a lot. I just need you to remember that what it means is tiny particle of matter. Sometimes the word particle will describe atoms. Sometimes the word particle will describe molecules. Either way, when we use the word particle, what we're talking about is a little bitty piece of matter. So why not, Matt? What would happen? Oh, it's
So I made some for a sensory experience, and I'd put it in, it was in a container, like a food container, put the lid on it, and I left it for like a week or two. It was probably the worst smell I've ever smelled. And I
Got
have,
a little
I've smelled
bacterial
some pretty
action.
stinky stuff.
Yeah, you
It
got
was-
some bacteria and fungi that were starting to break that down. All right, so back to states of matter. Remember that these tiny particles and things are always, 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 always moving. There is no matter that isn't moving a little bit, even something really solid like my computer mouse. It looks solid, doesn't look like it's moving, but the particles inside it are, at least they're vibrating. Kinetic energy is what we call that energy of motion, that vibration or movement of the particles. So the more kinetic energy something has, the higher its temperature is, and the more its particles start moving. And the opposite, the less kinetic energy a substance has, the lower its temperature and the less its particles move. So in this picture, as we go from the top to the bottom, from here to here, kinetic energy is increasing. This has very little kinetic energy. This would be a solid. Those particles aren't changing place with one another. They're simply vibrating. In a liquid, though, they're able to move around and flow past one another. It's all to do with temperature. So there, that's a gas. That's going to be even more. Kinetic energy has gone up. Movement of the particles has gone up too. Now, remember that particles are always in motion, even in solid things. That's important to remember. A lot of what we'll learn this year is based on that. Get that into your head. Even when something doesn't look like it's moving, the particles in it are. The motion of particles is such an important thing in physical science that it has its own name. The motion of particles is called thermal energy. So thermal energy is the movement of particles, and it is the term that we use to describe it is thermal energy. So gas has high thermal energy. Solids have low thermal energy. So which state of matter has the most thermal energy? Solid, liquid, gas. Yep, it's going to be gas. Gas has the most thermal energy. Solid has the least thermal energy. Just be sure that you understand what kinetic energy is and what thermal energy is and how they're different from one another. They are not the same thing. Kinetic energy is when the object itself is moving. Now, thermal energy is a kind of kinetic energy. It's basically the sum of all of the kinetic energy in a group of particles. So you can kind of use either term, but to keep things clear, it's usually better if we use the term thermal energy when we're talking about the movement of particles and kinetic energy when we're talking about the movement of things. Now, there's a little catch, which there often is in science. This little catch is what we call absolute zero. Absolute zero is the temperature at which all thermal energy stops. All particle motion stops. it is 0 Kelvin, or about 459 degrees below zero in Fahrenheit. Now, the thing about absolute zero, it's impossible to reach. It's theoretical, right? So we do have a theoretical temperature at which all particle motion stops, but it's not a real one. Matthew.
So we're solid, correct?
Actually, we're mostly space.
Oh, no.
But
Because what I was gonna ask
and-
is if like even theoretically, if we got hot enough, would we like melt into like a puddle of goo?
yeah. So you're mostly water. The human body is about 66% water. So if you got hot enough, that water would evaporate off. It's kind of a gross thought here, but yeah.
Would we be able to then like literally completely evaporate, like turn into a gas?
Eventually, yeah. If you could get a living thing hot enough, it would go into. We're not exactly cucumbers, but yeah, you can see that. Yeah, you can get it to combust, to evaporate away, and there would probably be some ash left, but not completely. All right. So back to states of matter. So the most basic classification scheme of states of matter has 4 to it. It has solid, liquid, gas, and plasma. Now, what's really interesting is that of all of these, we don't talk about plasma very much. In fact, most textbooks don't talk about plasma, but just a little tiny bit. But plasma makes up 99% of all the matter in the universe. Anybody know why?
Because shape shifting.
No, I didn't hear what you said, Evan. Josiah?
I think it's like in our blood. I think it's like in blood. I think the plasma.
Oh, yeah. So there's a different kind of plasma. This is funny. This is where science gets a little bit confusing because we do have plasma that is the liquid portion of our blood. It's not this kind of plasma. It's the biology plasma, not the physics plasma. Okay, they're 2 completely different things. It's like the same name for 2 completely different things. So the plasma that makes up 99% of matter is, you guys got it, stars. Matter exists as plasma in stars, and stars make up 99% of the universe. That's why there's so much more plasma than there is anything else. But we don't have a lot of plasma on Earth, which is why we really don't talk about it when we're talking about a physical science class, because we're learning about the Earth. So plasma is a lot like a gas, but it's a little different because it has more energy than gas does. So I want you guys to imagine a gas that's kind of like the air that you breathe, where the particles are all moving around really quickly. Well, in plasma, those particles have even more energy. They have so much energy that the particles themselves start to break apart. So when a gas gets really, really hot, or if you put in some kind of an electric field, the atoms that are inside start losing some of their electrons. Those free electrons and the leftover atoms, what's left after the electrons leave, which we'll learn later are called ions, they create a mixture that acts a little bit differently than a normal gas does. And that's what we call plasma. It's this mixture after the free electrons have left, after they've gone, because there's so much energy in the system. So we do find plasma in some pretty cool places. We find plasma in the sun, other stars too, where it's super hot. Lightning bolts and neon signs have plasma in them. Flames have plasma. That's one place on Earth where we find plasma. Another place that we find plasma is lightning. Lightning is made up of this supercharged gas, so it becomes a plasma. Science fiction plasma cannons are so powerful. Yeah. Has anybody ever seen the Northern Lights, the auroras? They're beautiful. So auroras are made of plasma. They're absolutely beautiful. Welding arcs. So what you see when the spark from welding, that's made of plasma. Like I said, neon signs are made of plasma. So there's low pressure gas inside the tubes of these neon signs and fluorescent lights. So a fluorescent light generates light when collisions of plasma happen and the electrons bump into each other. So this will all mean more as we go into our class, but kind of want to give you the idea here. So like I said, the sun, the sun is an example of a star in its plasma state. And this is called a plasma ball. Do any of you guys have one? Plasma ball is a fun toy to play with. Yeah, yeah. So if you haven't seen a plasma ball, I have one. I'll hold it up here for you guys to see. Let me turn it on. So you can, I'll put this back behind it. You can see the electricity kind of flowing around inside there. But when I touch it over here, can you see that now? How it, I know the light is reflecting, but you can see the electrons that are being kicked off of the atoms that are inside that plasma. They find a real easy path through my body. So they're moving through my body down into the floor. That current is what makes those strings. So there's this electrode, this high voltage electrode right in the middle. That's the stick right in the center there, that high voltage electrode. And that creates energy. And it puts out a lot of energy, and that makes plasma inside there. So the strings are the current flowing through the plasma. Now these electrons don't want to be near each other. Remember, electrons all have a negative charge. So they want to get as far away from each other as they can. So they're jumping all over the place, trying to get away from each other as much as they possibly can. So when I touch this plasma ball, the electrons inside the ball push into my hand and they flow through me to the ground. So I see this strand of light right there. It's pretty cool. Pretty cool. You know what's interesting? I have a sink that goes on and off with a wave. I wave my hand and my faucet turns on. When I turn my plasma ball on near my sink, it turns the water on. Not even touching. It's shooting electrons out into the air, and those electrons are activating my good question. They're activating my sink. Yeah, good question, Mel. What would happen if I let me see the question here. What would happen if it cracked? If it broke, it wouldn't work anymore, Michaela. Yeah, it wouldn't work. It would, the gas would just be released out into the air. It has to be contained. Also depends on the socket it's plugged into. Can you get burned by one? You can if it's a really powerful one. One that's like this, like the toy kind, you're not going to be able to get. At some science museums, though, they have very large ones. You touch the very large ones and your hair stands on end. If you've ever been to a science museum, you might have seen that. And if somebody comes up to you, you're touching the plasma ball, you touch someone else, you'll shock them because of the transfer of this. All has to do with electrons moving from one place to another. Mel.
So theoretically, what would happen if, say, you took one into space and you were floating and you touched one?
I don't know the answer to that question. I don't know. You'd have to have electricity, first of all, so it would have to be plugged into something to generate that power inside. If I took one of these into space, you mean? I think it would still work because the inside is sealed and it's a vacuum. It's sealed and it's got, well, it's not exactly a vacuum, it's got gas inside. Yeah, interesting. So you'll notice if you ever take a look at any of these plasma balls, they come in different colors. Anybody know why? Why do you think plasma balls come in different colors? How come some of them are, yeah, what do you mean the gas? Be more specific. Reaction of the gas with the plasma. Yeah, but why different colors? To answer that, we have to go back to our friend, the periodic table, because different gases, when you run this electricity through them, will produce different colors. Yeah, there you go. So neon is right here on the periodic table. Neon produces a reddish orange color. So if there's neon inside the ball, it'll be reddish orange. Argon produces a bluish violet color. Krypton produces a white streamers that look a little bit like lightning. Helium is often found in the bigger ones like you would find in a science museum. Xenon is usually also found in larger museums as well. And, oops, sorry, nitrogen also is one that produces like a grayish pink color. Matthew.
So because there's like gases and it's kind of like a vacuum in there, if I took one to space, if it was like one of those that was battery powered, if I turned it on and I didn't have the casing on it and I tossed it into the vacuum of space, would it like shoot out electricity?
Remember what electricity is. Electricity has to move. It's the movement of electrons. When the electrons are so spread apart like they are out in space, nothing can spread, nothing can pass through them. So you can't send electricity through the vacuum of space. So I think nothing would happen in that case. Okay, so states of matter: solid, liquid, gas, and plasma. There's actually a lot more. Oh, Luke says, can you put all of them in a ball? I don't know what would happen, Luke, if you put them all inside the same ball. I don't know if anybody's ever tried that. Yeah, it would be interesting to give that a try. I don't see anything there that would. So the noble gases are these over on this side. We'll learn they don't react. They're called noble because they don't react. They have all the electrons that they want in their outer electron shell. So they're not likely to have a reaction with anything else. Now, nitrogen will react, but since these don't, I don't think there would be, my hypothesis would be, if we mix these all together in the same ball, nothing would happen because none of those gases are going to react with each other. So maybe you'd get a bunch of different colors in there. I don't know. It's pretty cool. Pretty cool. If you touched it in space, would you just fill up with electrons? Well, remember that electrons are going to move. So when I do this, I don't fill up with electrons. The electrons are moving through me. They're just finding an easier path than out into the air. They're finding a more direct path. That's why this is drawn to my finger. They find a direct path and they just move down into the floor. So it's not like my body's building up electrons, although it is a little bit. There's a little bit at which it's building up electrons. That's why if I had a big enough one, I would shock somebody because the electrons would build up in me and jump over to them, but not indefinitely, not indefinitely. Okay, so plasma is like this supercharged gas that's full of energy, and it has parts that break apart and zip around trying to get away from each other really fast. The thing is, there's more states of matter than just those four. Scientists have discovered some exotic ones under real extreme conditions. Here they are. There's the Bose-Einstein condensate, a time crystal, neutronium, quark, gluon, plasma. Those are extra states of matter. They're not part of our course. You will get to them if you've ever taken advanced college physics class.
Are we part of like, I think they're part of like space-time.
Sometimes. Yeah. So we live here on Earth. We like to study the matter that we find here on Earth. And plasma is rare on Earth because it takes lighter elements to make it. And most of the free wandering gas is found out in our atmosphere. And the conditions needed for plasma to form are not met in our atmosphere very often. Only when there's lightning are those conditions met. But it is found in those few places on Earth. So we talk about it a little bit, but then, we're going to stick with the solid, liquid, and gas because those are the ones that we deal with mostly here on Earth. Like I said, Josiah, it's very complex. You could look it up. That'd be a good thing for you to do a little bit of research, finding out what time crystals do. They are a very exotic form of matter that are formed under very extreme conditions. And if you want to take an advanced physics class sometime, you'll get there. All right, so here we are again, states of matter. Now we categorize these by the energy of the particles at normal temperature and normal pressure, right? So we can change them from one state to another by changing the temperature or changing the pressure. Those things affect the arrangement and the energy of the particles. Sorry here. So there they are. You can see them moving around based on particle arrangement, based on energy, and based on the distance between the particles. So you can see there in a solid, the particles are arranged very nicely. They're orderly. They're very uniform. And there's not a lot of energy. They're just simply vibrating. and there's not very much distance between them. They're packed real tight together. In a liquid, like in a glass of water, think of that, those particles can move around. The arrangement is such that they can flow over each other. They can trade places with each other. There's more energy in them, and there's a little more space in between them. The distance is a little greater. In a gas, they're real far apart. They're very active. They have a lot of energy in them and a lot of space in between them. So solids tend to be fixed in shape. So this isn't going to change. This is going to stay this shape unless I add temperature to it. If I increase the temperature, I could melt it. I could turn it into a liquid, but it would take pretty high temperature to do that. Liquids, they have a certain amount of volume. Their volume isn't going to change, but depending on what container I put them into, they'll change shape. So they flow into the container that they're going to be in. And then gases don't have any fixed volume. They don't have any fixed shape. They're just simply going to expand to fill their container. And if the container is the room, those gases are going to fill the room. If you could see all the gases that are in the room with you, you'd be shocked. There's a lot of them. There's oxygen, there's nitrogen, there's carbon dioxide, there's water vapor. There's lots of different gases that you have in the room, but they're so far apart from one another that you don't see them. You're just looking at the individual atoms or molecules. So solids are one of the states of matter. They are packed tightly. They vibrate, but they don't move out of position. They have a fixed shape and a fixed volume and very low kinetic energy. They're not moving. What would happen if you fill cars with helium? That'd be fun. The floating car. I don't think so. All right. So I'm gonna scoot ahead here because I want to talk about liquids next. So this is why liquids can flow, because those particles slide over each other. The particles are actually changing place and flowing over each other. They've got more kinetic energy than they do in solids, but less than they do in gases. So right there, you can see the things about them. They're attracted to one another, so they come back after coming apart. So you can see this here. They're attracted to one another. These water molecules, the liquid molecules are attracted, so they tend to come back together. That's why they don't just go off out into space. I like this little cartoon. Liquids take the shape of the container while maintaining a constant volume. So that's it. Cats are liquid. Phase change joke, right? All right. Now, the more pressure we put on a container of gas, the smaller its nature is going to be, its volume is going to be. So the less pressure we put on it, the greater its volume is going to be. So gases don't have any fixed shape. They don't have any fixed volume. The particles are very far apart and they move around freely, and they're not bonded to other particles around them. So they can be compressed. Gases have more kinetic energy than liquid and a lot more kinetic energy than solids do. So right here, you can see what the molecular thing of a gas would look like. All right, there they all. That's all of them. Remember that term, thermal energy. That is the term used to describe the kinetic energy of moving particles. So a change in thermal energy causes a change in state. All right, here's a riddle for you. Before I am born, I am a liquid. When I am alive, I look like a solid. When I die, I am a gas. What am I? Before I'm born, I'm a liquid. When alive, I look like a solid. When I die, I'm a gas. Any guesses?
Star.
No, not a chicken. Here you go. A bubble. A bubble. When I'm born, I'm a liquid. When I'm alive, I look like a solid. And when I die, I'm a gas. And here's another cute one. I was water before it got cool. All right, now, how does thermal energy move? Thermal energy, this is another really important concept to remember. Thermal energy always moves from something hotter towards something cooler. It's going to move from something warmer towards something that's cooler, always. That's the way thermal energy moves. It moves from something warm to something cool. When thermal energy increases, water changes phase from solid to liquid or liquid to gas. And that phase change is due to increase in thermal energy. And there's three kinds of it. There's melting, energy's going up, vaporization, energy's going up, sublimation, energy's going up. Let's look at them here. Melting. You have a solid. It's a real easy way to remember all these is think about ice and water. That's such a common substance. We know about what it is. So if you can think, what does it look like when ice melts? Ice is going from solid to liquid when it melts. That's melting, solid to liquid. Then when liquid water again, think about your glass. What happens when the water in your glass evaporates up into the air? Hear that? Evaporate. It's becoming vapor. It is vaporizing. Vaporization when it goes from liquid to gas. But look at this. Sometimes things can go from being solid to being gas without becoming liquid in the middle. So this is what happens when your ice cubes in your freezer get really, really small. If you ever noticed that you get tiny little ice cubes in there, they didn't melt. They just sublimated. They went from being solid to being gas without going through the liquid state. Now, we also have it the other way. When thermal energy goes down, water changes phase from gas to liquid or liquid to solid. Again, think water when we're right here. Condensation, that's when gas in the air, water vapor in the air condenses onto leaves or onto the side of your glass. You call that condensation. Then when you've got liquid water that's freezing, it becomes ice cubes. It becomes solid. But in the same way, we also have a process where we go from gas to solid without going through liquid, and that is called deposition. We'll talk a little bit more about those. I'm going to pause right here because I want to start talking about this. I want to make our oobleck, our non-Newtonian fluid. So as you're, well, I'll do that after. So I'm going to tip my screen down so that you guys can see this and see how you make it. All right, I've got all my supplies here. There we go. All right, so I have a cup and a half about of cornstarch here that I'm going to pour into my bowl. Cornstarch the powder can get everywhere, but it's really easy to clean up. You just wipe it up with a wet towel. And I have, hold on, I forgot to bring a spoon. Let me see what I've got that I can use. All right, I'm just going to use my little back scratcher fork here. That'll stir really nicely. All right, so I can, what if you've got your water, you should have about a cup and a half of cornstarch and about a cup of water, but don't pour it all in. Pour just a little in and kind of see what happens. Pour a little bit in and then start to stir. And you'll notice right away that it kind of feels like hard to stir. It gets a little bit chunky. Keep adding your water a little bit at a time. Don't add more than 3/4 of the cup of water because I'm already starting to see the non-Newtonian Matthew. That's funny. Fun sensory science. Yeah. All right. So I've already got a little bit right here of the non-Newtonian nature of this. So I'm going to put a little bit more water in and stir a little more of the cornstarch in to get a larger amount of that. You guys will realize how hard this is to stir. That's because it has what's called shear force. So the shear thickening of the fluid means that it stiffens as you stir it. Now, it's not really a solid. We're not really making a solid. That's why it's called a non-Newtonian fluid, because it doesn't really behave like a solid or liquid. It's got properties of both. So at the places that you're applying force, the place where you're trying to stir or move it through your fingers, the cornstarch particles get mashed together, and that traps water molecules between them. So this oobleck temporarily turns into a semi-solid material. But we're still not completely sure about all the details. It is weird, and scientists don't really understand exactly how it works. we don't really know whether or not the cornstarch particles actually touch one another. We don't know what causes them to move apart after you take the pressure off. We don't know if we could have different sizes of grains of the cornstarch, if that would affect it or not. But we just know it's kind of fun to play with. So I've got a little pile of it right here. I'm going to take my hand and pick some of it up. And for those of you who are not able to do it, I want you to watch here what's happening. So this is liquid in my hand. It's pouring. I'm pouring it from one hand to the other. But as soon as I start to stir it, it becomes like a solid and I can make it into this ball. So I'm going to make a ball. Yeah, Evan's got it happening right there. Yep. So if you can pick up a little wad of it and have a ball of it right there. Can you see how I've got the ball? And the ball is, I have to keep pressing it though, in order to keep it into a ball, because the second, let me see if I can let you see that. Yeah, see how it's like a ball in between my hands. But watch what happens the very second that I quit putting pressure on it. It turns into a liquid and it runs through my fingers. Right onto my onto my mat there. Yeah. So this gets its name from a Dr. Seuss book. There was a show called, or a book that he wrote called Bartholomew and the Oobleck. And there was a gooey green substance that fell from the sky and wreaked havoc on the kingdom. So they call this Oobleck after him. But it's actually a good, it's a good example of what's called a non-Newtonian fluid. So right there, see how this is maintaining its shape? That's because I don't have quite enough water in it. Parts of it are getting liquidy, but if I add the rest of my water, or at least more of my water, then I can see how it, I think I'm going to try all the rest of the water here. If you add too much water, it won't become a solid. If you don't add enough water, it won't become a liquid. So it's kind of fun to play with. Can you guys think of any application for, this is what's called a shear thickening fluid that gets stiff when stress is placed on it? Can you think of a time when you might want something to be kind of fluidy, but then get real stiff when it goes under stress? Okay, I got a nice big ball right here. Now, you can see this and watch what's going to happen with this big ball as soon as I take stress off of it. Liquid pours right back through. It's really fun to play with. Yeah, so Ellie has some color in hers. I didn't put any color in mine. Speed bumps, that's an interesting thought. So like slow people down?
Well, more like what I was thinking is they actually are doing it in some places where if you take like a rubber, like inner tube sort of thing, and you fill it with, and it's really, really long and it goes across the road and you fill it with something like oobleck, then if you go over it slow, it's like you're just rolling over like a puddle or something.
Wow.
But if you go hard, if you go fast over it, because you're hitting it at high velocity, it seizes up, and it'll do the same thing as a normal speed bump, but it won't hurt. It won't damage the car if you're going slow.
That's really fascinating, Matthew. I've never heard of that before. I'm going to have to look into that. A couple places, though, a crash protection in a car is one area that they're looking into using a non-Newtonian fluid. Bike helmets. If they could put this in a bike helmet and it would become more solid, it might offer more protection. Think about a bulletproof vest. If it was more liquidy, when the bullet hit the vest, it would immediately, that sheer force would turn it into a solid. It would stop the bullet from going. You probably use a non-Newtonian
Inflatable
fluid.
bulletproof vest.
Yep, a bulletproof vest. You guys probably use a non-Newtonian fluid every single day. Can you think of something that you do every single day that you use every single day that's not exactly a solid, but not exactly a liquid? Toothpaste. Toothpaste is an example of a non-Newtonian fluid. It is particles in suspension. So it behaves a little bit like a liquid. It can be squeezed out of the tube, but it's a little bit like a solid in that it doesn't just go to liquid all through the on your toothbrush. Something like oobleck in my hockey helmet. Really? All right, that's interesting. Yeah. Mercury. No, Mercury is an element all by itself, and Mercury is a little bit different. Mercury is one of the only elements that is liquid at room temperature. Yeah,
I have
so
a question.
very good
How do you
question.
clean this off?
Just with water. Go to your sink and run it right down your drain. It just goes. You can dump your whole bowl full, whatever you make.
No, my
that's-
hands.
Your hands too. You can just rinse them with water. Class is almost, in fact, class is over now. So you can keep playing with your oobleck for a little bit more. If you want to add some food color to it like Ellie did, it's kind of fun.
It's already putty.
If you watch this for a minute now. If you got it in a bowl that you can do this with, if you take your fist and hit it, it won't, well, it's kind of splashing a little bit now because I've got a little bit too much water. If you don't have too much water, it'll make, it'll stop your hand and it won't splash. But I added a little bit too much water to mine, so it's not gonna do that. It's pretty cool stuff though. It's pretty fun to play with. All right, this was a great class. Thank you all for your participation, your great questions. If you have any others, send them my way. Have fun with your oobleck. I'll see you next week. Bye, everybody.
Thank you. Have a
coming.
nice week.
Thank
Happy
you.
Labor Day.
Thank you.
Bye.
You too.
Thank you.
Liberty, liberty, liberty.